I work mostly with discrete genetic events and things that I like to call admixture graphs, which I will show you an example of, that most people here will have seen something like this. And I want to do three things in this talk. I want to show you how to calculate joint spectra analytically on a mixture graph. It's easiest to understand what's going on in a situation where there are no new mutations in the graph. What that means for me is that you're already polymorphic at the root, and that's the first part of the theory you need to get. Then I want to show you how you can extend that to mutations which arise more recently in the root of the tree. That's part A I'd done some time ago. Part B I doubt if you've seen. And finally I'm going to give an application which is not so different from Laurent's application, but I'm going to go over it a bit more slow, I think. Now, I would say that I've been actually working sort of off and on this for several years, and I still don't regard the work as mature. There are lots of technical difficulties, some of which Laurent actually mentioned, things like convergence, and I don't feel I have a reliable and robust inference engine that I want to release to you yet. But so this is very much work in progress, although it's been work in progress for quite a long time. Okay, so I'm not going to try and formally define a mixture graph, but here's a fairly complicated example. You've got a root of the tree where you should really think that there's a constant. You should think the root is fairly ancient, and that there's a constant size population more ancient than the root, because I'm not modeling anything there. And then you get. There are two sorts of edges in the graph, and most of them are what I call drift edges, in which allele frequencies are simply changing in frequency by diffusion down the edge. I'm going to assume throughout this work that you have constant size population on each edge, right? So what that means is that the calendar time and what constant size population you've assumed to determine the actual drift. And then finally, you have other edges like this, which correspond to admixture events. And it's sort of fairly obvious intuitively what this means. But what this means, if you pick a random allele in W, it has probability alpha of having instantaneously come from B prime, and probably 1 minus alpha it came from the other population. So this is a point event happening instantaneously in time. And the reason I like these events is not because I think they're mathematically, I think they're biologically or historically correct. It makes the mathematics easier, at least for me. So this apparatus is not able to deal, say, with migration events where you have low-level migration occurring over significant periods of time. That's a different thing. All right, so two sorts of graph edges, admixture and drift. And I just want to briefly remind you about some diffusion theory results. Most of you will know this stuff because it's not, this is sort of what I think of a Kimura theory, elementary diffusions on the right Fisher diffusion. But here are some basic facts and notation. So the first is the ground rules. I've got neutrality everywhere, no selection, and no double or back mutations. So if you see a derived allele in two places, there was an ancestral mutation event, and that's important. I think this is not a bad assumption on genome-wide human data, though there are certainly some difficulties there. we have an ancestral population, and this is, I'm just trying to get, so imagine you have one edge on my tree. So you have an ancestral population X, a descendant population Y, here's some drift, T generations, and the population size is N. So the standard diffusion timescale is you say that the drift time is tau, which is T over 2N. So on the diffusion timescale, coalescence occurs at rate 1, which is why that we do this. And I like to write the transition function for the White-Fisher diffusion. This is your frequency x at big X, your frequency y at big Y. The drift is tau. And if you're polymorphic, so y is on the open interval 0 and 1, this transition function, which I call the Kimura function, is the probability density of your you are at y conditional on you were at x. Okay, so this is all just basic notation. So some facts about diffusion that we are using all the time. Diffusion's a Markov process. If you know where you are now, that determines the future, and the past is irrelevant. And the diffusion is a martingale, so the expected value of the frequency in the future is the frequency now, and that's true for all future time. Then, next fact, you fix out in finite time almost surely. That's really an important property of the White-Fisher diffusion, and you actually need to think about that. It's not entirely trivial to prove that, at least for me, but it's an important fact. And I also need repeatedly the classic polymorphic spectrum for population of constant size, where the way you think about this is I'm looking now, and back in time, some mutations are occurring at a very small rate per small time. So in some tiny interval, there's a very small probability, epsilon delta t, that a mutation occurs, and I'm interested in the probability distribution of the allele frequency now, and Ewens proved in the 60s that if you look at the, I'm assuming I'm polymorphic here, and you integrate over all the possible times back where the mutation could have occurred, and normalized by epsilon, the spectrum is 2 over y. So you get this for the derived spectrum. So that's analytic, and it's very helpful in some of the other things that I'm doing here. All right. So here's something that most of you, some of you, like Yun Song there, will know this extremely well. And people who've worked on diffusions know this result, but they probably don't know it in this exactly presented this way. So we've got, again, I'm just looking at one edge on the tree. We've got ancestral population X, descendant population Y. And I'm interested in expectations of polynomials in Y. So f of y is a polynomial, and my notation is I'm interested in the expected value of f, conditional on the allele frequency being x in the parental population. And some facts. This expected value, e sub x, is a polynomial in x. And I just want to get back to the same space. I've got polynomials in y, ex is a polynomial in x, so change x to y to get me back to the same space. The map f going to e sub f is linear. And if you have a linear map, it's natural to wonder what the eigenvectors are. And the answer is the eigenvectors are the polynomials 1, y, and then the polynomials y times 1 minus y times Jacobi polynomials, which are a family of orthogonal polynomials. And the corresponding eigenvalues are 1, 1, and then this e to the minus lambda I tau, where lambda sub I is this combinatorial thing, I plus 1, I plus 2 over 2. Now, this is a thinly disguised version of Kimura's theorem, which gives you an explicit formula for the transition function of the Wright-Fisher diffusion. So this is simply Kimura's work in the 1950s, mildly repackaged. Right. Okay, clear enough so far. So this gives me, the first thing I want to do is write down a calculus for writing down E sub x. Right, and okay, and so here it is explicitly. You take your polynomial f of y. You can write it in this form. You pull out the constant and linear terms, then you're left with a bunch of stuff that's got to be degree at least 2. You arrange it that everything's divisible by that f of 0 and f of 1 are, you arrange f of 0 and f of 1 to kill the behavior at the boundary, and then you get this lifting formula where the constant and linear terms just lift straight off. The linear term lifting is just a restatement of the martingale property when you think about it for a microsecond. And then you get this Jacobi polynomial expansion, and you have to multiply by the relevant eigenvalues. This is a completely explicit lifting formula that allows you to lift any polynomial back one edge. Right. Okay. So in our admixture graphs, we also have these admixture edges, and I'd like to know how to lift that. And this is completely trivial. What I'm doing here is I've got a polynomial in little u, and I'm interested in lifting that back to polynomials little s, little t. And all I do is I substitute alpha s plus beta t for u, and I get a new polynomial in s and t. I've eliminated u. Right. So I told you how to lift the drift edges. I told you how to lift the admixture edges. Right. Those are the basic ingredients for the algorithm we need. This is analytic stuff. All right. So now we come back, and this you'll see is not millions of miles away from what Laurent was doing. I've got a mixture graph. I've got a whole bunch of what I think of as leaf populations, and the leaf populations are populations which I'm thinking of as populations now, they're current populations, and I'm observing counts of the derived and ancestral alleles on the leaf populations. So I'm going to introduce a variable x sub I, which corresponds to the derived allele frequency in each allele population. Just for notation, y sub I is 1 minus x sub I. And so you have this binomial formula for the probability of seeing a particular count vector. I see a bunch of counts C, the complementary counts are D. This is just binomial theorem for what the likelihood is of seeing those counts, conditional on my variables at the leaf. And what I want to calculate is a likelihood of these counts conditional on a frequency R at the root of the tree. Right. So, I've got some mess here. There's a frequency little r right back here, right? I ought to be able to calculate the probability of seeing these counts down here, conditional on R. Remember that our ground rules for now are no new mutations. Right? So no new mutations arose on this tree down here. All right? And it's now rather clear what I do. I have this polynomial in leaf variables x, right? I pick one of the leaf populations, and I apply my lifting rule, right? That will get rid of the leaf node and give me a polynomial involving variables that are higher up the tree, right? And so you just repeatedly do this. You keep each time after I've lifted one node, I can then kill that edge. I find a new leaf variable, keep on lifting. I get back to a polynomial in one variable R, right? Lifting all the way back to the root. And by Ewan's theorem, the likelihood of R is proportional to 1 over R. So my entire likelihood comes down to this univariate integral, E sub R over R. Right. And that's what I do. I just I take my count data, I take each possible pattern, I apply this lifting formula, I get back to the root, I do this univariate integral numerically. So it's worth comparing this with Daddy. I don't want to do a detailed comparison, but clearly we're sort of working on much the same problem, right? Both this work and Daddy are trying to compute likelihoods. The detailed flavor, though, is completely different. Daddy likes continuous migrations, right? I don't. Daddy wants a small number of populations, but doesn't really care if the counts sizes are rather large, right? Because the work is going on there. The sort of working fluid, if I could say it for Daddy, is directly the joint spectrum of allelic probabilities. And here, this is sort of being indirect, right? I don't get these x's directly. I'm integrating them out all the time, right? So that's a different thing. So my running fact times get bad if I count data is very deep, and I think that's not true for Daddy. But they don't get so bad if I have lots of populations, right? That's a entirely different deal. I do think that some of the problems I have are identical to problems that Laurent had and Daddy. I mean, Carlos is sitting in the front row here. There are some difficulties for me in convergence. There are especially difficulties in determining what the right phylogeny is. And that's actually my main interest. I'm not so interested in getting the parameters tight, though that would be nice. But I would like to get the shape of the graph roughly right. If you haven't got that right, it's all sort of nonsense, really. All right. So this is step one, and it's machinery where you've got no new mutations. So what about new mutations? I was quite puzzled by this for some while, but eventually I managed to work out what the theory ought to be, I think. So now I've got some atomic event, drift x goes to y, and I'm interested in the event that a mutation occurs on this edge E. And again, f of y is a univariate polynomial in y, and for technical reasons, and it's always true in practice, I want it divisible by y. And population size on this edge is n prime, where it was big N back at the whole root. Okay. So here's a theorem. The probability of m times the expected value of f conditional on m is, first of all, there's a factor here which involves the population sizes. And then you've got this function q f tau, which is this thing. There's a term involving f of 1, which is the related to the fixation times the drift, and then this integral where we're going to calculate the expected value of f conditional on x integrated over x. Although notice that this is sort of a funny thing because the mutation actually occurred on this edge, and I'm worrying about functions involving what didn't happen, right? Because there wasn't an allele frequency. X was all derived, but nevertheless, I can mathematically consider what happens when I do this. So this is a formula which may actually be new. I mean, someone in the audience may tell me they've seen this before, but I certainly have not. I won't try and prove this rigorously, but I'm gonna mumble how this happens. So you imagine a phylogeny. You've got x goes to y, and then you just got a constant size population all the way back to infinity here, with the same size of population as occurs on this edge, right? Just imagine this phylogeny, and now the event that a mutation occurs on this edge, right, has the probability that an event occurs ancestrally somewhere, minus the probability that it occurs ancestral to x. Right? You can just write it that way, right? Huh? And then you work through what that means, right? And that difference, both those things can then be calculated, right? Ewan's theorem tells you what you expect just given the mutation occurs ancestrally somewhere, and my calculus allows me to work out the expected value of f conditional on x. That's the previous case, and you get the answer you want. This is almost a kind of physicist's argument. There's a thing you want to do, and you construct a situation that isn't what happened, but allows you to do the calculations you want, right? And that's good enough, right? So that's it's a slightly curious thing. All right, so
you're making no assumptions about whether the mutation is fixed or segregating, right? It just arose on that branch.
Yes, and
you'll deal with the bookkeeping.
So let's just. Well, I'm only going to mumble about it, really. But really, what happens is we keep on lifting up, right? And now we get to a situation where y is a leaf node, right? Well, two things can happen. First of all, there can be variables around in my polynomial which are not y, right? What that means genetically is that there are populations where the allele cannot be ancestral to y, right? So that doesn't happen, right? Right? If, in other words, if there's some variable here that isn't y after you've lifted up here, the configuration you're looking at did not occur from a mutation on this edge. Right? So the only case of interest is that the polynomial is univariate, right? And then I'm telling you how you calculate this quantity, probably the thing times the expectation. Right? So what happens in the big picture now is that you still want to calculate the whole likelihood, and there's a whole bunch of scenarios depending on whether the mutation was polymorphic at the root or on which edge it occurred, and you can add all these things up. Right? So this is the new ingredient you need if you're going to have to deal with novel mutations.
It's just sort of a flux of new mutations coming in at different parts of the
tree.
Yeah,
but by ground rules, on a given base, the new mutation can only occur once in the tree. Right? You just have to worry about where it happened. Okay. This is a calculus that allows you to deal with, at least in principle, arbitrary count joint allelic data on any admixture graph. Right? And there are three kinds of variables. There are drift parameters on the edges, there are admixture weights, and there are population sizes on edges where new mutations can occur. Right. Huh? I think this is implicit in what everybody's doing, but it hasn't always been, I think, terribly explicit, that the population sizes, the drift is critical to everything that's going on here, but the actual population sizes are not important at all unless new mutations are arising. Right. So if you're trying to specify sort of calendar time and population size, but you haven't got any new mutations occurring on the stage, the whole thing is ridiculously overparameterized. I mean, it doesn't make any sense, right? So you may as well just think about the drift. All right. Okay. So now I want to, in the last part of the talk, I want to show you some data and some at least mildly new ideas for thinking about this. And this is actually definitely overlapping with Laurent, though I'm going to talk. It was a fairly small part of Laurent's talk, and this is a larger part of what I want to do. So what I want to say, first of all, is if you take nothing away from my talk, you should take away this picture and what it means. So what we're looking at here is the polymorphic spectrum in Yoruba, right? Conditional on a single archaic derived allele. That's either Neanderthal or Denisova, and you get this extremely symmetric U-shaped curve. And the first thing to say is that there seems to be absolutely no difference between whether you condition on the Denisova fossil or the Neanderthal. But that's actually not quite the whole story, because this is a conditional spectrum, and you could ask the probability that Yoruba is polymorphic. And it turns out that that's very different when you condition on Denisova or Neanderthal. Yoruba's got a 2.5% smaller probability of being polymorphic if you condition on Denisova than on Neanderthal. That's beyond significant.
Would it be like you multiply the probability by 97.5%, you subtract 2.5%?
No, you multiply by 97, about 0.97,
Okay.
0.975, yeah. So this is really a very striking fact, and in our recent paper on actually Svante's paper on the Altai Neanderthal, we look at this rather carefully and argue that this is extremely strong evidence for what we call superarchaic flow into Denisova. I think that there is some extremely ancient gene flow into Denisova, which we could perhaps loosely call Homo erectus, who knows. So there's the supplementary paper here. David and I worked on this, Svante's group worked on this, Monty's group worked on this very hard. But I don't want to talk about what we did there. The interest in that paper was what was going on the sort of archaic part of the tree. So I want to think about what's going on in the modern human part of the tree. So the fact that you get this same conditional spectrum, I think, must mean that the conditional spectrum at the split, when ancestral Yoruba and ancestral archaic split, it can't matter if Yoruba is polymorphic. If you're polymorphic at that split time, the spectrum must have been the same whether you're conditioning on Denisova or Neanderthal. Or there's no way we're going to get this complete matchup.
It's not complete, they're different on the left.
Yeah, that's true.
Those are, I mean, those are the points we have.
So I should say that I'm trying to here to get a crude picture of what's going on, and this will not be true in absolute detail, right? And in fact, for example, as an indication of the sort of problems I don't want to talk about, we believe that there is very low level West Eurasian gene flow into Eurasians. Into Yoruba, sorry. There's West Eurasian gene flow into Yoruba at a very low level, carrying some Neanderthal alleles with them. And that's exactly what I don't want to talk about. It's sort of, I'm trying to get the big picture right, and so details are going to be washed under the rug a bit. All right. Furthermore, the spectrum is extremely close to symmetric. So why is that? Again, it's not exactly symmetric, but all right. So if you remember in fact, it comes from Ewan's theorem. You've got 2 over x as the stationary distribution, and multiply by x because we see a derived allele. The polymorphic spectrum should be flat at split time under simple phylogenies. And I think, when I've thought about this fairly hard, about the only way you're going to get an approximately symmetric spectrum down here is that's what happened. So I think that the spectrum at split time is extremely close to a flat distribution. Well, if you think about your diffusion theory, polymorphic spectra that are uniform stay uniform under constant population, under panmictic. So if the Yoruba spectrum, ancestral Yoruba spectrum is flat at the archaic split time, and all you've got is panmictic mating since then, the spectrum has to stay flat. And I put it to you, this is not a flat spectrum. So this is already extremely powerful evidence that there's got to be something more complex going on. And I think that Laurent mentioned that he's seeing evidence for ghost populations, and Mike Hammer and Jeff Wall. Is Jeff in the audience? I haven't seen him today. Or maybe he left. Pity. Oh, I was hoping he'd see this. But a couple of years ago, Mike Hammer and Jeff Wall, using entirely different methods, haplotype-based methods, claimed that there was ancient gene flow into the Yoruba. They weren't able to date it very precisely. And what I'm saying here is that it seems to me that there's overwhelming evidence that what you must have had is a deep split and then merge back in the Yoruba lineage, but it's more recent than the archaic human split. So I like to say it's an ancient event, but not an archaic event. Right? Furthermore, as you'll see from the actual parametric models I'm going to write down, I just show you one fit. The effect is really pretty extreme. All right. So once you do that, it's rather easy. Once you allow yourself this deep split emerge, fitting the spectrum is quite easy, and the parameters are poorly determined, which I think is probably true for everyone's techniques, actually. Right? I can fit this with many models that are different in detail, but they all have this deep split and merge. And here what I'm doing is I'm looking at the Yoruba spectrum. I condition on a single het in Yoruba using David Reich's SNP arrays and Denisova derived. And this is good data on the fit. You can hardly tell the difference. All right, so now here are 2 models. One of the interests here is how do the rest of your humanity fit into this? So 2 models. Model A, we have this deep split in Yoruba, but the out of Africa event only occurs on one of the branches, right? I mean, what's the evidence that actually the split and merge are more ancient than out of Africa? And the second one is you get a split and merge in the Yoruba, and then the out of Africa event is occurring after the merge back. These are two very, very different models. Notice that both of them have exactly the same Yoruba spectrum because okay. So, and if you pick just a single French allele and try and fit these things, I can fit both the models fit very, very well, which is again a cautionary tale that phylogeny is not trivial to determine. So finally, I want to wind up with a new idea, which I think could be used really by anyone working in this area. I think it could probably be used by Laurent and by Carlos' group in using Dardi. Suppose you've got any of these models, you've got a branch off B, and then you've got some phylogeny down here for Eurasians, which is occurring just independently of whatever's going on down in Africa. It's not a very unusual situation. And suppose we have suppose we're going to study a fairly small number of Eurasian alleles. Well, and we're in a situation where we're not having to worry about new mutations. Notice that if I condition on Yoruba polymorphic and archaic derived, I absolutely don't have to worry about new mutations because the mutations I'm looking at are all very old. All right. So let's suppose I'm just going to consider 3 French chromosomes, okay, and a whole bunch of Yoruba. Well, when you think about that, when you go to coalescent, you've got 1, 2, or 3 distinct lines of descent at the branch-off point, okay? And there's some probability for that, which I'll call U, right? And that probability, and in fact that event for how many lines of descent I have when I coalesce back, is completely independent of the Yoruba phylogeny. Nothing to do with it, right? I'm going to, but I can observe the probability of J-derived French alleles given K Yoruba alleles. Okay, and so given the Yoruba phylogeny, I have some probability P for the allele frequency at the branch-off point. And so you just write down you can just write down some trivial equations here, and you see that this joint allele spectrum for French and for French conditioned on the Yoruba is just these expectations, where the U's are independent of K, right? And you've got these P's that you don't know, but where the dependence on K comes in. But the P can be calculated using exactly the calculus that we have. Right? For example, you want to know probability of P and Q. Well, just attach 2 notional alleles to the branch-off point with no drift and run your calculus, or run Dardi, and you will read off what the expected value of PQ is, right? So you can calculate the expectations in here, the coefficients of U can all be calculated with the machinery you've got. And that will be true for Laurent, it will be true for Carlos, it is true for me, right? And at that point, we can just run standard linear regression to fit the UI. Well, that's actually very powerful, because what it means is that I can just run a regression machine, which is instantaneous, and I don't have to worry about the detailed phylogeny on the Eurasian side, right? So I think this is quite a strong idea, and it allows me to think about the phylogeny on the Yoruba side and not make detailed assumptions on the Eurasian side for small numbers of alleles. So this is not going to work if the number of alleles you're observing on the Eurasian side is large, because you start having to worry about all the ways you can partition up N, which is growing exponentially. But I think that there's a lot of inference that's important here that can be done with quite small numbers. So I did this, French n equals 3. for model B and model A, and this is not actually a very impressive looking picture. What I'm showing you is normalized residuals for Yoruba frequency conditioning on het for 0 through 20, and green is the model B and red is model A. You may not be very impressed, but actually these are normalized so that at random the mean value should be 1. We expect the actual mean, if we're right, to be a bit smaller than 1 because we did a fit, right? If we knew truth, it should be 1, but I fitted, so I'll do better than 1. And what I see is that model A, I have a mean square residuals of more than 2, and model B is less than 1, and that's pretty decisive.
So,
Yeah.
shouldn't we be concerned about the systematic pattern in the residuals?
Yeah, well, I told you, yeah, you should. And I'm not writing down the likelihood here, right? I'm just telling you that the mean square residual is about right for model B and much too high for model A, right? And the dependence is coming in from all kinds of stuff. First of all, phylogeny is probably wrong, right? Then there's dependence in the original count data, right? And so on.
I mean, just because you've got one model that is less terrible than the other model, but you've got systematic residuals.
Well, the problem is that I'm not correctly modeling the covariance on the residuals.
Yeah.
That is true, and that's one of the, I began by saying this is a work in progress.
Yeah.
Right? No, absolutely. And in fact, I want to come back to my final slide. I want to come back to the problems, which are many. So here's a fitted model, model B, and it's really rather an extreme model, though I see this Denisova split. My current apparatus on this data does not allow me to estimate this particular drift. Right? These are drift parameters in normalized time times 1,000. Right? So on one branch, I have deep drift. Right? With a great deal of stuff fixes out on this edge. I have extremely shallow drift on this other branch. And then 60-40 mixing, right? Not much happens on the Yoruba branch after the merge, because we actually have every reason to think that for the last 100,000 years anyway, the Yoruba population, effective population size has been quite big, and this is the out of Africa event. So this is, of course, the ghost populations that are being that Mike Hammer and Laurent have seen. And if model B is right, this stuff is going to be ancestral to all humans except maybe for San. And I'm looking at the San right now, and I'm not sure what. I'm still not quite sure what's going on there. So here's what I think is some of the things which are missing in the methodology. So the first one, I think actually the most important, is testing for model adequacy. I think, with respect to Carlos and Laurent, nobody really knows how to do that. I don't know. I mean, the problem is, actually Carlos said it, you do a fit, right? This fit is better than that fit, right? But is it good enough, right?
That's super easy to test, simulate data and see what's good as a fit. It's not a hard thing.
I mean,
deviation's larger than what you expect.
With respect, I don't agree. In fact, this is a problem this is a standard problem of statistics. Let me give you a trivial example. You have univariate data, and you decide you're going to fit a normal distribution, right? And it has a mean zero variance 1 very closely, right? and you get happy, right? And you generate other simulated data and find that you have that you're.
Well, it's like something if it doesn't fit.
Yeah.
No,
Some
no.
other model it.
No, but the point.
As a minimum, you should show that the model.
That's
fits it
true,
in.
but it's by no means adequate.
No, so what we
There
did,
can be gross. The point is, there can be gross features in your data that show conclusively you're completely wrong.
Right. So that's why
And-
you fit the model to one aspect of the data and you test with another. So one thing we did in the Daddy paper, for example, is we fit to the joint allele frequency spectrum and then look at whether the model predicts the patterns in the decay of LD, which is a statistic. We make no use of the LD information.
That's
and then for some models, for example, you can say, oh boy, it did a terrible job of predicting the decay of LD, and this does a much better job.
Yeah.
And for
But-
example, when we were fitting admixture for Mexicans,
Well, perhaps I'm not trying to knock Daddy here, but I really.
No, that's fine.
My personal opinion, this is an unsolved problem. I mean,
I think statisticians have thought a tremendous amount about ways that you can do model selection and model validation with orthogonal.
And in complicated situations, it's an unsolved problem. Maybe we should talk about this offline. But it's even. I mean, I'll tell you. I'll be able to make a somewhat extreme statement, but I've actually checked with probably the world authorities on this. It's an unsolved problem how to test whether multivariate data is multivariate normal. Look, there is no agreement as to how to do this. So
Sign estimators are a problem, right? We can think about.
It's really hard. So I do not know how to build phylogenies, and again, I think this is not. This is related, of course, right? I've got a phylogeny. I can certainly test if somebody else's phylogeny looks better than mine, but is the data really? Have I got it right, or is there something that tells me that it's wrong, or what other phylogenies are possible here? Right. I mean, so I think this is hard. The data, in spite of David Reich's and others' efforts, the data is not as good as I would like. By the time you're looking at many populations, the data gets thin, and it becomes problematic. The local maxima can be difficult, but I suspect that Carlos went into that too, actually, to some extent.
Yeah, no, the convergent stuff is a real problem. And the more data you have, the finer the grid has to be, so that you can compute the likelihood better. I mean, more data makes the problem much harder.
Yeah. Actually, my thinking on that is maybe we can inch up on the problem, and if you use less data, your models are coarser, and that actually may help you for convergence. And so you
Kind of simulated annealing kind of approach.
Yeah,
So when you start getting into an area that has more data.
And finally, in real world, you do have double back mutations, you do have sequencing data, you do have the ancestral allele being misidentified, and this stuff doesn't do any of that properly yet. I've had many. This is only a very partial list of my collaborators. David Reich, of course. Sriram has been a great help with me here. He's part of this workshop. Monty and Eric have worked on related fields, and I talked a great deal about data that came from the Neanderthal and Denisova consortium, which, of course, led up by Svante. So, and finally, I would like to put up an advertisement. David Reich's lab has a whole bunch of talented postdocs who scare me because they're so strong, and we have 0 graduate students. And I would like to fix this. So thank you very much. Monty.
Well, your model, I think it's model B, where the admixture event, yes, that one takes place before the split of the Arubans and the French, makes some strong predictions about the French conditional spectrum as well.
Yes, I
Is
haven't
that
really looked at
consistent?
it's. I'm looking at this. It's not as clear because if you look at deeply, first of all, you've got to worry about the archaic admixture coming in, which
Right, but that has a predictable.
which is but it also the bottleneck sort of wipes out memory to some extent, right? So a deep bottleneck means you can't go back through it really, because this is such an extreme event that perhaps we can do something. I haven't really studied that. Yeah. Yeah, Andy.
Sort of a philosophical question, but you had all these very strong caveats at the end about the model being unable to test model when the model was adequate, and yet you seem to be confident that Model B fits better than Model A.
I feel, it's related to, I'm not, okay, I am moderately confident. Right? I mean, I really think the residuals of the Model A are too large. Right? I mean, even if I look at one of my boxes, I've already got 2 sigma, and that's not, it's not ridiculous. But
it's like you believe there's a monotonicity, so this is true under the wrong model. Under the correct model, maybe the residuals of Model A.
well, if Model A with some refinements I don't know, I might be okay, right? Right? That's correct. Yeah. So I'm not entirely confident. This is definitely defending myself. This is definitely work in progress, right? And I notice I haven't published it. Yeah. That's it.
Any more questions?
Well, I don't want to delay your lunch anymore.
All right, thank you again.